All right, welcome to your last video of Module 1. So this is part 1.5, and for a majority of this lesson, we'll be going over what a one-to-one function is. All right, so previously we talked about invertibility. We said, is this function invertible? And essentially for the purposes of this class, one-to-one is going to essentially mean invertible, right? If it's one-to-one, you can take the inverse of it. So a one-to-one function is a function where each input has a unique output. To put it another way, every time we plug in the value of x, we will get a unique value of y. The same y value will never appear more than once. That's essentially the what I want you to take away. The same y value will never appear more than once. Okay, so example 1 says determine if the function, I'm not going to read it off, is a one-to-one function. So if we look here, think about the idea that the y value cannot appear more than once. So if we look here, first off, it is a function because none of the x values repeat. And then it is a one-to-one function because none of the y values repeat. So yes, this is one-to-one. And that's because none of the y values repeat. So example 2 says determine if this function is a one-to-one function. So first we'll look, okay, first off, is it a function? Yup, none of the x values repeat. Then is it a one-to-one function? Well, let's look. Oop. We've got 2 -9s as y values. So no, this is not one-to-one. And why is it not one-to-one? Well, the y values repeat. The next question says, is f of x equals x minus 4 squared plus 2 1-to-1? So let's go ahead. Let's graph this. All right. We look here. I graphed x minus 4 squared plus 2. And if you recall, the rule is that you cannot have y values that repeat. Another way to look for this is doing that horizontal line test that we talked about, right? If you do the horizontal line test, you can see here that this fails the horizontal line test, right? If we were to draw horizontal lines, they would hit the function more than once. So this function is not one-to-one. Okay, so we could put that down. No. It is not 1, 2, 1. So I want to show you real quick. If we were to take the inverse of this function, okay, I'm going to show you what the graph of that looks like. So the inverse of this function looks like this. Now, if you recall the vertical line test, right? In order for something to be a function, it needs to pass the vertical line test. And if we were to draw lines going up and down on this blue graph, it would hit it more than once, right? So essentially what happens is the inverse of the red function is actually not a function, right? It fails the vertical line test. So it says, how can you restrict the domain so that there is an inverse of the function? All right, so that the inverse of the function exists. So let's think about this. I'm going to go ahead. This is our original function. And if you notice at the vertex, that's kind of where everything starts to double, right? It goes to the right, goes to the left, and you have double y values. So let's think about what would happen if we restricted it so that we only had x values starting at the vertex. All right, so I set it so that the x values are greater than 4. All right, so now this function with the restricted domain is one-to-one, right? If we did the horizontal line test on this function, it would pass. We'd only hit each point once. Now let's go ahead and graph the inverse of that. Well, the inverse of that is a function. Right? Now we've got something that actually is a function. It passes the vertical line test. So essentially what we can do is restrict the domain so that the x values are greater than 4. So we could say domain is going to be 4 to infinity. All right, so this way we do have a one-to-one function to begin with, and then the inverse is a function. So to reiterate, to tell us something is a function, you're going to do the vertical line test, right? That's something that we learned, a couple years ago, the vertical line test. It tells you if something is just a function, right? So like if we have something like this would pass the vertical line test, right? It only hits it once. However, we have, is it a one-to-one function, right? So if we were to draw another parabola, well, no, it's not one-to-one. That's the horizontal line test. So we have the vertical line test to tell if something's a function. We have the horizontal line test to tell if it's a one-to-one function, okay? All right, so this next section says determine whether the relation is a function. If the relation is a function, state whether the function is one-to-one. All right, so remember, in order for something to be a function, the x values cannot repeat. So if we look here at 1, we can see that the x values do not repeat. All right, we have one output for every input. And in order for something to be one-to-one, the y values cannot repeat. And again, we only see the y values once. So this one is, in fact, 1, 2, 1. All right? Then for this next one. Again, in order for something to be a function, the y values cannot repeat. And if we look here at 3, this 3 does repeat. It has 2 different outputs. All right? So this one is not a function. It has an x value that repeats, so it's not a function. All right? If we look at this next one, none of the x values repeat. So it is a function. Then we have to say, okay, is it a one-to-one function? Well, clearly, this y value repeats. It repeats 4 times right there. So you would say it's a function, not 1, 2, 1. Make this thinner. All right, next one. Is this one a function? No, it is not. The number 2 repeats. So you would say not a function. All right, so let's take a look at some of these graphs. So I just want to reiterate, there are 2 tests we do. To find out if something is a function, we do the vertical line test. To find out if something is a one-to-one or invertible, we do the horizontal line test. All right, so first let's find out if these things are functions. So we'll go ahead, we're going to do the vertical line test. So if you see here, this line does pass the vertical line test. It is a function. All right, it only hits each line once. So we've got that this is a function. So now let's find out if it's one-to-one. So this one again passes the horizontal line test. So this one is a one-to-one function. All right, let's try this one. So this one's a quadratic, right? First, let's find out if it is a function. So we do the vertical line test. All right, so this one is a function. It passes the vertical line test. Maybe I'll do a different color. Let's see if it is one-to-one. Ooh, this one is not one-to-one. It fails the horizontal line test. So this one is a function, but not 1, 2, 1. All right, is this guy a function? All right, we passed the vertical line test. Is it one-to-one? Yes, it is one-to-one. Each line only hits the function once. So we would say it is a function. 1, 2, 1. All right. Is this guy a function? Looking good? Looking like a function. We only hit the function once. Is it a one-to-one function? No. This line actually hits it 3 times. All right, it fails the horizontal line test. So you would say function, not 1, 2, 1. All right, is this guy a function? No. It fails the vertical line test. You would just say not a function. Is this guy a function? No. Fails the vertical line test. You would just say not a function. All right, last one. Is this guy a function? Also fails the vertical line test. Not a function. All right. So now let's go ahead. We're going to go ahead and try to solve these 3 problems. They are on your Ready, Set, Go, but I kind of just wanted to go over them because I figured a lot of you guys would have questions about them. So before we get started, I wanted to review a topic. It's the idea that you can rewrite something under the radical as an exponent, right? The number inside of the radical goes in the denominator and the power goes in the numerator, all right? So we can go here and we can rewrite these guys as powers. So we'd have our base that we start with. The power goes in the numerator. The number in the radical goes in the denominator. Same thing here. 3 is going to go in the numerator. 7 is going to go into the denominator. Then we know that when we multiply things of the same base, we can add their powers together. So we would do 2 sevenths plus 3 sevenths. So we get 5 sevenths. So it would just be x to the 5 sevenths. All right, so number 4. Now, usually when you have something like this, one goal should be to try and get all of these numbers in the same base. But looking at these, we cannot get these numbers into the same base. 32 is a base 2, 9 is a base 3, and 27 is also a base 3. So let's go ahead and let's just see what happens when we put them into their bases. So 32 is the same as 2 to the 5th power. 9 is the same as 3 to the 2nd power. And 27 is the same as 3 to the 3rd power. Now, when we rewrite this as a power, we would end up with 2 to the 5 over 5, which is the same as 2 to the 1st, or just 2. 3, we get 3 to the 2 over 2. Now, remember, for square roots, this has an imaginary 2 there. 3 to the 1st, we get a 3. Turn this guy into a power, we get 3 to the 3 over 3. 3 to the 1st, we get a 3. So we get 2 times 3 times 3, which would give us 18. All right, then the last one. Another rule, we multiply our when you raise an exponent to an exponent, you multiply them. So you would get 7 to the negative 2. And a property of exponents is that when you have a negative exponent, you can boot it down into the denominator. So you get 1 over 7 squared, which would give you 1 over